Welcome everyone. Let's continue on chapter 12, section 4. Today we're going to talk about cross product. So far we've talked about the dot product of two vectors, and the result of that was a scalar. It was a constant value. Today we're going to mention that by the definition that we will provide, the cross product of two vector A and B will be a third vector which has a property that is orthogonal to both vectors A and B. So that's basically the construction of the vector C. Where it comes from is from that. So let's assume two vectors A and B are given. We can assume in 3 dimension, A1, A2 and A3, because in 2-dimensional, if you have two vectors, you cannot create a third vector that is orthogonal to those two. So we assume it's in 3 dimensions. And vector B is given B1, B2 and B3. We're looking for a third vector C such that dot product of A with C as well as the dot product of the B with C is 0. What does it mean? The dot product is 0. That means the angle between these two are 90 degrees. Between the vector A and C. The angle between the vector B and C are 90 degrees. It doesn't say anything about the angle between A and B. And we assume A and B are non-zero vectors, and they are different vectors, not parallel to each other. We will get to that in a bit, but this is basically the idea of defining the vector C. So if we look at this definition, A dot C would be basically this equation. And since we want that dot product to be 0, we set it equal to 0. B dot C would be this equation, product of all the components, add them up, it must be equal to 0. You can find the solution for this equation by multiplying and simplifying. There is no unique solution, but you can pick the solution to be in the form of C1 equal to that, C2 equal to this, and C3 equal to that. If you check by replacing C1, C2 and C3 into these two equations, equation 1 and 2, you will notice that it will satisfy both equations. That means that you will get 0 on both sides. So that tells us that C1, C2 and C3 are the components of the vector C, in which it would be orthogonal to both vector A and B. That's how basically the definition of the cross product comes in. So here, the definition. If A is given, the vector A and vector B are given, then the cross product of the two vectors is the vector C, in which, by the way, the cross product, this is not an X, this is multiplication. Normally they write it this way to use cross product. So A cross B would be a third vector, where the third vector are exactly the C components that we found. Then the property of this third vector C is that it's orthogonal to both A and B. It's a very useful tool to find the equation of plane, for example. There are some applications to it that we will get to it if we come back to this section. Okay. So here's an issue. Memorizing these entries, these components, are always difficult. So we try to write this cross product in terms of matrices. And if you're not very familiar with the matrices, that's okay. We only want to discuss it for the determinant of matrices, and that's not something complicated. So let's assume you have a 2 by 2 matrix. 2 by 2 matrix means you have a square matrix. It has two components, A, B, C, and D. Sorry, 4 components. It's a 2 by 2, 2 row, 2 columns. And the determinant, normally instead of writing this, they will write a straight line. That would be the determinant. And what does the determinant calculate? Determinant calculates the product of the diagonals minus each other. So A times D minus B times C. That's how we define the determinant of a 2 by 2 matrix. So AD minus BC. And this is just a number. Okay, so this is the determinant of a 2 by 2 matrix. How about determinant of 3 by 3 matrix? You assume by picking the first entry multiply by, if you remove the first row and first column, what happens, you will have a 2 by 2 matrix. So the first entry, A1, multiply by the determinant of the leftover, if you remove the first row and first column, minus, so that would be A1 times determinant of the submatrix B2, B3, C2, C3. And then what if we pick the second entry, A2, you remove the second column and first row, then what you have is now this submatrix that contains B1, C1 and B3, C3. So it would be minus, the sign would be alternating, plus, minus, plus, minus. So the first one is positive, second one would be minus A2, second entry, multiply by the determinant of this leftover, B1, C1 and B3, C3. And similarly, if you pick A3, it will be plus A3 times determinant of leftover, removing the first row and last column. Whatever number that you pick, if you pick the row 1, third column, you remove the first row and third column. So the submatrix leftover would be this submatrix B1, C1, B2, C2. If you calculate now, you can calculate this submatrix determinant. It would be B2 times C3 minus B3 times C2. That multiplied by A1, and so on and so forth. So the determinant of a 3 by 3 basically is an extension of the determinant of 2 by 2 matrix. Let me get rid of these lines. Okay, so this is basically the idea to extend it. For 4 by 4 you can extend this ID. Okay, but we only need the 3 by 3 and 2 by 2. So for example here, let's calculate the determinant of this matrix. So what you do is, you pick the first entry, 1, multiply by the determinant of removing the first row and first column. Determinant of 1, 3, 1, 1. So this would be the submatrix left over, if you remove the first row and first column. If you pick this term, this entry, so minus 2 times, you remove the first row and the second column. And what is the leftover submatrix is basically, let me go back. Sorry about that. Minus 2 times, the leftover matrix would be 0, 3, 2, 1. And then plus, if I pick the last entry, negative 1 times determinant of the submatrix leftover would be, if you remove the first row and last column, what is left is 0, 1, 2, 1. So there is no memorization behind this, you just calculate. And now this submatrix, so equals 1 times the submatrix here would be, multiply the diagonals, subtract from each other. 1 times 1 minus 3 times 1. So 1 times 1 minus 3 times 1. If it's number, you shouldn't write this, you should be able to do it in your head, but I'm going to write it just to make sure everyone follows. So here, 0 times 1 minus 3 times 2. 0 times 1 minus 3 times 2. And plus, negative 1 times 0 times 1, 1 times 2. 0 times 1 minus 1 times 2. There is always subtraction between the multiplication of the diagonals. And now this is just a number. You can calculate, this is 1 times 1 minus 3 times 1, that is negative 2 times 1, so this would be negative 2. Here you would have negative 6 times negative 2, positive 12, and negative 1 times negative 1, this would, times negative 2 would be positive 2. So the sum of these three would be positive 12. So we found out the determinant, which is positive 12. Okay, but The use of this determinant to find the vector, the orthogonal vector C, is quite nice. So here, let me shift this up maybe a bit. Okay, if we look at this matrix A cross B and write down the product, what you get is if you write the first row to be the standard vectors I, j, and k, what you have is I times A2, A3, B2, B3. Again, this is assuming we're doing cross product of A and B. The submatrices would be minus j times A1, A3, and you would have B1, B3, plus k times the submatrix left is A1, A2, and B1, B2. I'm not going to write everything down, but let's look at the first one. You would have I times, what would be the entry? It would be A2, B3 minus A3, B2. Actually, let me write everything down so you would see. J times A1, B3 minus A3, B1. And here you would have k times A1, B2 minus A2, B1. Okay, so let's focus on these. This is gonna be the third component of a vector because it's multiplied by k. This would be the second component of a vector multiplied by this negative as well. And this would be the first component of the vector that would be calculated through this cross product. But if we compare this, if I scroll up a bit, and if we compare it with here, with this highlighted section, the first component, if we do the cross product, we get A2B3 minus A3B2, A2B3 minus A3B2, A2B3 minus A3B2. The second component, there is a negative there, so it would be basically A3B1 minus A1B3 because this negative would be distributed. So A3B1 minus A1B3, and you will see that the second component here would be A3B1 minus A1B3, and similarly the third component. So instead of memorizing this cross product, you can always go through this determinant. Calculation of this determinant will give you exactly the cross product. Okay. So do not try to memorize cross product. Try always to write the standard vectors I, j, k in the first row, and then A in the second row, and the component of B in the third row. It is important that you do not interchange the order of these two. If it's A cross B, then you have to write A in the second row, B in the third row. If it was B times A, then you would change it. B would be in the second, A would be in the third. Because the result would be quite different. It would be opposite of each other in terms of signs. Okay, so here, as an example, given A and B, find out A cross B. And again, notice that A cross B, you expect a vector. You do not expect a scalar. A dot B will give you a scalar. A cross B should give you a vector. So A cross B would be, I'm going to calculate this determinant A, I, j, k. A first, 1, 3, 4. B in the third row, 2, 7, negative 5. And then write down the determinant 3, 4, 7, negative 5 plus minus j times 1, 4, 2, negative 5. I'm removing the second column and first row, plus k times removing the first row and third column. You would get 1, 3, 2, 7. You can try to memorize that formula, but it would be there is a higher chance that you make a mistake if you memorize it than just writing it down. I times this, the determinant would be, let me change this color to red. That times that minus this one times that. 3 times negative 5 is negative 15, so it would be negative 15 minus 4 times 7, 28. And you'd have minus j times 1 times negative 5, 2 times 4, minus 8. You have to always subtract this minus that. Plus k times 1 times 7, minus 2 times 3. Okay, so what do we get? Is basically negative 15 and minus 28, that is 30, 40, 43. So negative 43i. Minus 5 minus 8 is negative 13. Another minus would be plus 13j and plus 1k. So therefore I found the cross product. What is the cross product? A cross b. You can leave it as ijk, or you can write it as component wise vector. There we go. And the property of this vector is that it's orthogonal to both a and b. You can check that by doing dot product. This is one way to check, would be if you calculate a dot, this, let's call this c, to see what we get. Actually, let me change this to go back to green. So let me call this vector c. A dot c must be 0. Otherwise, we've made a mistake. So let's calculate a dot c. It would be 1, 3, 4 dot with negative 43, 13, and 1. So negative 43 times 1 would be negative 43. 13 times 3 would be 39. And 1 times 4 is 4. You'll see that this is simply 0. That tells you a dot c was 0, therefore a and c are orthogonal. As a test, try to calculate b dot c. And this should end up to be 0 as well. Means b and c are orthogonal. That means c is orthogonal to both a and c, a and b. Again, this doesn't mean that a and b are orthogonal. This only means that if you have two vectors like this, there is a third vector. This is a, that is b. There is a third vector that is orthogonal to both of these two vectors. That's what it means. This is the cross product a cross b. Can call it C. Okay, I think maybe the order I wrote it is not right. A here, B there. There we go. Okay. There is a theorem that if you calculate A cross A, you would get 0 for any vector A. And the reason for that is, if you write this determinant ijk, A1, A2, A3, A1, A2, A3, then you would get I times A2, A3. I'm gonna only do the I term. You can calculate the J minus J, whatever, and the K term. But look at this matrix, this submatrix. You would have A2, A3 minus A3, A2. That is simply 0. This determinant would be 0. 0 times I would be 0. Similarly, you would get 0 for j, 0 for k. So you will end up with the vector 0, 0, 0. It's not a 0 constant, it's a 0 vector. Okay, so if A cross A, if you're calculating A cross A, then the result is simply 0. You don't really need to calculate that. And as I mentioned, if you calculate A cross B and you get a vector C, then C is orthogonal to both A and B, which means the dot product of the cross product with A, this is C. C must cross dot product with A must be 0, and C dot product with B must be 0. This is something that we started the definition with. One more theorem. If theta is the angle between A and B, then A cross B, so let me draw this, maybe this would be easier. So if you have vector A and B, and theta is the angle between these two, then the magnitude of the cross product, which gives you some orthogonal vector. Let's say this orthogonal vector is the A cross B. It's supposed to be orthogonal to both of them. The magnitude of this cross product is magnitude A, magnitude B, sine theta, sine of the angle between the two vectors. It is very similar to magnitude A dot B. So if you remember A dot B, we would have magnitude A, magnitude B, cosine theta. But for the cross product, you get sine theta. This could be simply proven by writing this determinant and go through it. If you square both sides and simplify, use the dot product, then you can prove it. It's quite long, but it's possible. I think the proof is available in the book. What we care about is where can we use this? And it turns out that if you want to calculate the magnitude of A cross B, it is the same as the area of a parallelogram created by the vectors A and B. So let's assume you have vector A and vector B. Here is vector B. If you draw parallel to A, you would have this line, and if you draw parallel to B, you would have this line. So what you create is a parallelogram, and let's say the angle between these two is theta. Okay, so let me erase these again, so because I have to use a different color. Okay, so let's say if I draw an orthogonal here, what would be this height? This height basically would be magnitude of B times sine of the angle between sine theta, between the two vector A and B. That would be the height here. Draw the triangle, you would see that given the angle theta, this would be opposite divided by hypotenuse would be sine theta, so therefore the opposite side would be basically the hypotenuse times sine theta. And this is basically the height, the h. If you want to calculate the area of a parallelogram, it would be the height times the base. So height, which is magnitude of B sine theta, and the base would be magnitude A. So the area of the parallelogram should be B sine theta multiplied by magnitude of A, which is the base. And this is nothing but the cross product magnitude, exactly that. So if you have two vectors and they create a parallelogram, then the area of that parallelogram is basically magnitude of the cross product. So which is a useful tool instead of calculating the angle and figuring out what is magnitude B sine theta. You can calculate the cross product and that will give you the area. And something that you should notice, if vector A and vector B were on top of each other, which means they were parallel, you have no area created, so that means the cross product of these two must be 0, and that is something similar to what we talked about if you do cross product of A with A. Okay, this kind of tells you the idea that what happens if the two vectors are parallel, then there is no area, so the cross product must be 0. Okay, but as an example, let's say find the area of a triangle with the vertices of, so you have 3 vertices, let's call them A, B, and C. Okay, so you have 3 vertices A, B, C, and they ask you to find out the area created by these 3 vertices. And you might ask yourself, we haven't talked about triangles, we only talked about parallelogram. But you can think about this, if I would have had a parallelogram, then this triangle would be exactly half of that parallelogram. So if I calculate the area created by this parallelogram, then I can divide by 2 and that will give me the area of the triangle. What you only need to know is what are these 2 vectors. You just need to figure out 2 vectors with the same starting point. So you can assume B is the initial point of the 2 vectors, and I will create the vectors. Then I will create the parallelogram, find the area of that parallelogram by doing cross product, and dividing it by 2 will give us the area of the triangle. So I will say, okay, the vector AB or BA is basically the difference between the 2 endpoints, A minus B. So A minus B would be 1 minus minus 2, so it would be 3. 4 minus 5 would be negative 1, and 6 minus minus 1 would be 7. You do A minus B in terms of point, and it will give us a vector. This is what you get as a vector. And similarly, you can do B, C. and that gives us the vector c minus b, so it would be 1 minus minus 2 again, 3. Negative 1 minus 5 would be negative 6, and 1 minus minus 1 would be 2. So what do I need to know? I need to find out what is, if you call this vector u, vector v, I just need to find out u cross v and find the magnitude of that. So first let's find u cross v. That would be, write the determinant I, j, k, 3, negative 1, 7, 3, negative 6, 2. And this would be I times. It takes a quite while to calculate all these numbers, but it's nothing complicated. You just need to make sure that you write the corresponding submatrices correctly. Don't make any mistakes. And then we need to find out the magnitude later on by squaring the components and adding them up. Okay, so k times 3, negative 1, 3, negative 6. You would have I times, I'm going to do this, negative 2 minus 42. That would be minus 44 I. And 3 times 2 minus 3 times 7, that is minus 15j. And 3 times negative 6 minus 3 times, so that would be minus 15k. Okay, so what would be the magnitude? U cross v would be square root of 44, negative 44 squared, plus negative 15 squared, plus negative 15 squared. And whatever this number is, let's say something. Say star. You can calculate this using a calculator. So what would be the area of the triangle? The area of the triangle would be, because this is, we calculated the area of the parallelogram. Area of the triangle equals to whatever that number is divided by 2. Star divided by 2. I didn't calculate the end result. Double check the work, make sure that is correct, and try writing another example for yourself, see if you can calculate that. Finally, one of the important things about the cross product is the cross product of these standard vectors I, j, k. Notice the orientation that I mentioned in the very first section of 12.1. When you write the x's, you said this must be x-axis, that must be y-axis, and here is supposed to be the z-axis. You will notice the difference if you change the order. If you calculate the cross product of I and j, you will get the orthogonal vector k that is orthogonal to both of them. You can do this by simply writing down I as 1, 0, 0, j as 0, 1, 0, and calculate the determinant. What is important that if you put your fingers along I and rotate it toward j, your thumb should be upward toward k. That is very important when you calculate the cross product of I, j, k. This tells you in which direction the results should be. So if you calculate I times j, I cross j, you would get the vector A because your thumb would be upward. If you calculate j, put your fingers along j, curl it up toward k, where is your thumb pointing? It will point toward I. So the cross product of j and k would be I. On the other side, if you do k cross j, so it means put your fingers along k, curl it toward j, what your fingers is going to point toward, the thumb would point towards the opposite of I, so it would be negative I. So k times j, k cross j would be negative I. That's why the order really matters, how you multiply these two. Okay, so in order, if you multiply ij, you would get k. If you multiply jk, you will get I, and if you multiply ki, you will get j. If you change the orientation of the cross product, you'll get the opposite values. You'll get negative I, negative j, and negative k. As a practice, maybe calculate one of these try to calculate k cross I, see if you get the j. It's nothing complicated, it's orthogonal to both of them, and simply you'll figure out that every other submatrix will give you the determinant 0 except the corresponding jth one. And here is one thing that is important. We had this idea that if you multiply, you can interchange how you multiply. If you have A times B times C, it's not true that it's going to be equal to if you have A cross B cross C, it's not the same as A cross B cross C. This is very important. You can see it through this example. What is I cross I? Since I and I are parallel, the cross of these two would be 0 vector. 0 times I would be 0. On the other side, if you change the orientation and do I times I cross j first, you'll get the k vector. And I cross k, what was I cross k? I cross k is negative j. So I cross k here would give us negative j. And you notice that it's the same vectors I, and j, but how you multiply gives you different result. So it is not true that you can change the order of multiplication for the cross product. Be careful with that. And another one of the properties, there are a couple more properties, but as I mentioned, that if you change the orientation, it would be the opposite. If you A cross B, it would be negative B cross A. And if you have distribution, you can distribute. This is not an issue. A cross B would be distributed. A cross B, A cross C. Here's one important one. This is called the triple product, the scalar triple product or something like that. I don't really remember the name. But if you do A dot, this is dot product, with the vector B cross C, it turns out to be exactly the same as A cross B dot the vector C. You can prove this by writing down A as A1, A2, A3, B as B1, B2, B3, and go through all those calculations. You can show that this would be a through statement. Okay. It's a useful tool for calculating volume. I will show you in a second. But if you do this A dot B cross C and A cross B dot C, it's exactly the same value. And that value turns out to be a certain volume. And as a result of these triple products, which is not quite that easy to show, you have to go calculate all the combinations. You'll see that there is a identity that you can write the cross product in terms of dot product multiplied by the vectors B and C. So if you have A cross B cross C, you can write it as A dot C multiplied by B. The A cross A dot C is some constant. That constant times B, and minus A dot B times some times the vector C. These two are constants since there is dot product. So basically it would be dot product of these two multiplied by the other vector minus the dot product of these two multiplied by the vector C. Okay, let's see the application of that triple product A dot B cross C. And let's focus on a parallelepiped, which is basically a tilted box. So let's say if you have a box, let me draw a box. I assume it's the base or lengths are given. Let's say A, B, and C. Let me actually use different values. X, Y, and Z. Then what do you say for the area? For the volume. The volume would be basically the base multiplied by the height. The area of the base multiplied by the height. So you would say the area of the base would be X times Y, and the height is Z. This is assuming that everything is orthogonal to each other. So the angle here is 90 degrees. The angle between Z and the bases are 90 degrees as well. But what if you tilt this box? What happens? The same idea will hold to calculate the volume. The volume would be basically this base, the area of the base, which we have calculated. If you have two vector B and C, the magnitude of B cross C will give you the area of the base. And then if you multiply by the height of the box is what we need to calculate. So B cross C would be basically the vector orthogonal to B and C, which would be this red vector, and the angle that it creates with the vector A, let's call it theta. Then the height, corresponding height, would be basically magnitude of A times cosine theta. So if I want to multiply this by magnitude A cosine theta, this is basically magnitude A dot B cross C. Because magnitude A dot B cross C would be magnitude A magnitude B cross C multiplied by the cosine of the angle between, which is exactly what we have. But this magnitude, the result of the dot product is always a constant. So this magnitude is basically the absolute value, because you want the volume to be a positive number. So after you do the dot product, what you get is a number, and if it's negative, you take an absolute value, it becomes positive, which gives you the volume. So here's an example. Sorry, I redid this example just earlier on, and I forgot to erase the solution. So let me erase these stuff. Okay, so you're given 3 vector and they ask you to find out what is the volume of the parallel pipe created by these 3. So what you need to calculate is A dot B cross C. So first figure out what is B cross C, then do A dot, and at the end take an absolute value. This will give you the volume of the parallel pipe. I think there is an E somewhere. Parallel piped. I don't want to make a mistake. Okay, so let's figure out what is B cross C. B cross C. This would be I, J, K, and vector B would be 2, negative 1, 4, and vector C would be 0, negative 1, and 1. And if we do submatrices and calculate this, you would get I times negative 1, 4, 1. Just make sure that you pick these submatrices correctly. Don't make any mistakes, because the result would be incorrect if you do that. Plus K, and this minus sign is important. K times 2, negative 1, 0, negative 1. So what is this determinant? The determinant would be negative 1 times 1, that would be negative 1 minus negative 1 times 4, so that would be 3i, and you here would have minus 2j and minus 2k. So we found out the B cross C. So if we calculate A dot B cross C, would be vector A 1, 4, negative 3 dotted with the vector 3, negative 2 and negative 2, and that is simply 3 minus 8 plus 6, which gives us positive 1. So if this was negative, you would take an absolute value to give you the volume. So the volume of the parallel pipe would be absolute value of 1, which is simply 1. Okay, so we calculated the volume, and that is the use of that triple product. One thing that I didn't really specifically spend time on it was that IJ cross product. So if you multiply I and J, what you get is the K vector. You can always, you don't need to memorize it, you can always draw this and say here's I, here's J and K. So if I want to multiply I and J, I'll put my hand along I, curl it toward J. So what do I get is the thumb will be upward. Try this, make sure that you understand what I mean. So you put your hand in the fingers. Your fingers would be along the I direction, where your palm is toward J. So if you curl your finger, I kind of have to draw a picture. So let's assume this is your fingers, and if you curl it this way, your thumb would be upward. Okay, that's a bad drawing, but try maybe to look at the book that gives you a better picture. So the result of I cross J would be K. On the other side, if it was, for example, K cross J, you know the result contains I, but is it positive I or negative I? You can just simply say this is K, this is J, here's I put my hand along K, my fingers, I curl it toward J. So where is the thumb going? The thumb is actually going in the direction of opposite of I. So it goes in the other direction. It's along this direction. So it would be negative I. And you can use this to calculate cross product, because what you know is if I ask you to do I cross I, the same vector cross product with itself is always 0. If it was J cross J, you would still get 0. So let's calculate B cross C without doing the determinant matrix. You can do that as well. So vector B was 2I minus J plus 4K. What is the cross product of this with the vector C, which is 0I, you can write that 0I, ignore the I, minus J plus K, 1K. So if you do the cross product, what you get is 2I cross product with negative J, 2I cross product with, let me actually use parentheses just to make sure that you do not subtract, plus 2I cross product with K, and so I'm distributing this times that, this times this, and so on, minus J cross product to negative J, minus J cross product with K, and plus 4K cross product with negative J, and finally plus 4K cross product with K. Okay, so this is if you distribute everything. Some stuff are easy to simplify. For example, this J cross J, this is simply 0 because it's the same vector you do cross product, J and J. Ignore the constants. On the other side, K and K, 4K cross product K, this is 0 again, so I can ignore these. Now what do I have is these 4 terms left, and I calculate the cross product. 2I cross product with negative J. What is the cross product of I and J? The cross product of I and J is simply K. So I will get 2 times negative 1, which is negative 2, so I'll get negative 2K. Okay, for the next one, what is the cross product of 2I and K? So what is the cross product of I and K? I cross product with K would be if you put your hand along I, curl it toward K, where does your thumb go? Thumb goes outward actually toward negative J. So this would be negative 2J. Term I cross K would be negative J. So the 2 is still there. J cross I, that would be J cross I, did I write it? Here, K cross J would be negative I, so J cross I, J cross K would be positive I. So you'd have negative positive I, which is simply negative I. And plus 4 K cross J would be again negative I. Here, K cross J, you have 4 times negative 1, so you get negative 4I. Simply becomes positive 4I. And if you added up these two, will give you 3I. You have minus 2J minus 2k. This is another way to calculate that cross product that we did above here, and the result is exactly the same thing. The only thing is that you have to be careful with distributing. You should have like 9 terms if they all contain I and j and k, but the cross product of I, j, j, k, k is simply 0, so you can ignore those and you will have 6 terms that you have to calculate. Okay, so this is about it for this section. I'm gonna stop at this point.